Good afternoon, everyone. Today I'm going to talk about sustainable component for aerospace application for a green material chemistry project that presented by Group 6 consists of me, Azizah Salmaa Zuhairoh, Winda Arista Novelasari, and Khisya Pradipta Subagyo.
For decades, the aerospace industry has focused on performance, reliability, and safety. To meet these goals, we've used material like aluminum alloys, titanium superalloys, and composites. But here's the issue: while these materials work incredibly well, they come with serious environmental consequences like high energy consumption, significant carbon emissions, and a lot of waste that can't be recycled. Why sustainable materials matter? Today, the world is facing big challenges, from climate change and carbon neutrality goals to the demand for greener technologies. Aerospace is being called to adapt, not just by improving flight system, but by rethinking the materials we use from production to disposal. What are sustainable materials? Sustainable materials are designed to reduce harm throughout their entire life cycle. That means they come from renewable sources, take less energy to make, and can either biodegrade or be reused. This approach is not just better for the environment, it's smarter engineering. Let's look at a few examples. First, polymers like PLA or recycled thermoplastics. These are biodegradable and easy to process. Then we have composites made from natural fibers like flax or hemp, strong, lightweight, and with a lower ecological footprint. Metals like recycled aluminum or titanium reduce emissions, especially when produced with cleaner methods. And finally, ceramics made from industrial waste, they offer excellent thermal protection and address issues like toxic waste. So, why does this matter? Because these materials not only perform well, but they also help create cleaner manufacturing processes, reduce our dependence on finite resources, and align with global sustainability goals, especially SDGs 9 and SDGs 12. This isn't just about better materials, it's about being a responsible engineer. That's why the study focus that's why the study focuses on exploring and comparing sustainable composites, polymers, metals, and ceramics. We will look at their role, benefits, and challenges in aerospace, because understanding this material is key to build a greener and smarter future in aviation. We will talk about sustainable composite materials, especially biocomposites, and how they are being considered for use in aircraft, particularly for radome applications. A biocomposite is a material where at least one part, either the fiber or the matrix, comes from a natural sources. These materials are getting more attention because they're lightweight, biodegradable, and relatively cheap. So, what is a radome? It's basically a protective dome on aircraft that shields radar antennas from weather, aerodynamic forces, and even bird strikes. A good radome material needs to be taut and have a low dielectric constant. Traditionally, high-performance synthetic fibers like Kevlar and glass are used. Traditionally, high-performance synthetic fibers like Kevlar and glass are used, but now there's growing interest in natural fibers like banana, bamboo, kenaf, and pineapple leaf fiber. They offer similar mechanical performance but with a lower environmental footprint. In fact, these natural fibers have better dielectric properties ranging from 2.8 to 3.2 compared to conventional glass fiber. and their strength increases with longer fibers due to a higher aspect ratio. Of course, natural fibers aren't perfect. They absorb moisture and don't bond well with the matrix by default. But chemical treatments can help. They modify the fiber surface, reduce moisture uptake, and improve the fiber matrix bonding. Biocomposites made from natural fibers show great potential for aircraft applications like radiomes. With the right treatment and design, they can deliver the performance we need while also making aviation more sustainable. The wing box is the internal framework of an aircraft's wings. It carries most of the load during flight, so strength is non-negotiable. But the lighter we can make this part, the more efficient the plane becomes. Carbon fiber reinforced polymers are strong, but they are not renewable. They're hard to recycle and have a big environmental footprint. That's where sustainable alternatives come in. Buchler and his team explored this idea by modeling unwing bugs, but this time using natural fiber composites. They focused on Ramah fiber and the results were impressive. The weight dropped by around 12 to 14% compared to the aluminum version. Why Ramah? Because it's strong, stiff, biodegradable and lighter than traditional materials. That means less weight, less fuel and fewer emissions without sacrificing performance. So, the use of natural fibers is in aircraft wing box is more than just a green idea. It's an engineering solution that works. It's a step toward aviation that's both efficient and environmentally responsible. Now let's take a look inside the aircraft, specifically at the materials used for cabin interior panels. Ananjiwala and his team have proposed a green, sustainable approach using natural fibers. Cabin interior panels must meet multiple criteria. They need to be strong, lightweight, moisture resistant, and most importantly, fire safe. Ananjiwala's team tackled all of this by using woven flex fabrics and a phenolic matrix. Flex is biodegradable and affordable, but it has only moderate fire resistance. Meanwhile, the phenolic matrix provides good adhesion and heat stability. Together, they make a strong candidate for eco-friendly composite. To enhance performance further, they use a honeycomb core design, a technique already well known in aerospace. This structure makes a panel strong yet lightweight and also resistant to bending and buckling. But the big hurdle was meeting fire, smoke, and toxicity standards. Since flex is flammable, flame retardants like phosphates or tin compounds were used. This helped the composite meet FST regulations safely. In the manufacturing process, they first created flame-retardant flex-based prepregs, then sandwiched them with honeycomb cores. Finally, they used compression molding at 130 degrees Celsius for 75 minutes. In conclusion, the study shows that natural fibers like flax, when combined with smart design and fire treatment, can truly replace conventional cabin panel materials. They are sustainable, cost-effective, and aerospace-ready.
Next slide is sustainable metal materials for aircraft. As the development of space technology, it is urgent to reduce the weight of structural materials to improve the carrying capacity of payloads and comprehensive performance of spacecraft. Aircraft sitting alone was valued at 7.61 billion USD in 2024, contributing to 4% of global GHG emissions. Reducing aircraft weight by 1 kilogram can cut 0.90 4 kilograms of carbon dioxide emissions. Lightweight seating can save up to $200 million while complying with FAA standards. Magnesium alloys are promising due to their low density, about 1.73 gram per cc, high strength to weight ratio, and vibration damping. Compared to aluminum, magnesium alloys offer better fatigue resistance and structural efficiency. And the magnesium alloys allow them to replace plastic, offering greater stiffness while remaining lightweight. Research confirmed that integrating magnesium into aircraft and satellite structure supports sustainability and performance goals, labeling it as an green engineering material of 2000 to 21st century. Next, to improve the performance of magnesium alloys, researchers have alloyed magnesium with elements like aluminum, zinc, silicon, calcium, lithium, and rare earths. This alloy improves mechanical strength, corrosion resistance, and thermal stability while keeping the material lightweight, recyclable, and efficient for EMA sliding. For RA or rare earth material, with magnesium alloy, it will be AZ series or magnesium, aluminum, and ZN, AM series, AS series, and ZK series, while the super light magnesium alloys is about 1.35 to 1.65 gram per cc in density and 25% lighter than traditional Mg or magnesium alloys. It is the ideal for ultra lightweight aerospace and electronics. The series is LA, LZ, LT, and LX. Next. Next is the global use of magnesium alloys in aerospace industry. So the magnesium has a long history in aerospace. In 1970s until 16, the US used magnesium lithium alloys as structural parts, while United Soviet developed alloys as Ma-21 for lunar landers. In China, magnesium components are used in satellites and spacecraft. Beijing spacecraft factory overcame corrosion and welding issue. The G04 alloy reduced 30 kilo in Shenzhou 4. Shenzhou Tong University achieved for 20 until 30% weight saving in Mars probes component. Next, the use of magnesium alloys in the aerospace industry. First one is magnesium alloys in aircraft cabin. AZ31P magnesium alloys successfully replaced aluminum in ILX-27 helicopter components, passing 100-hour fitting simulation. So the magnesium alloy is good substitute for PA7 aluminum alloy to aid in the helicopter weight reduction. Next is magnesium alloy for satellite platform structure. Why we use magnesium alloys? Because it is 30% lighter than aluminum, like for satellite panel, and while aluminum is 700 gram and magnesium is 1500 gram. So the use is in the structural panels, electronic casing like light and EMI shielding, brackets, head pipes, tanks, skins, embedded parts. And the benefit for using magnesium alloy for satellite in platform structure is it is lightweight with good stiffness, radiation protection, surface treated magnesium still safe about 25% weight uh, versus the aluminum. This magnesium is high temperature straight alloy and magnesium form for ultralight panels is about 0.61 gram per cc and 5 MPa strength. Second, application of magnesium alloy in payloads. First one is antenna component. We use magnesium alloys because it's strong, stiff, lightweight, and thermally stable. Magnesium alloy offer high specific strength and rigidity. They can reduce antenna weight by 20%. And then this this magnesium is tested in space, like gold-plated magnesium antenna pass in 1-year space exposure test, and signal remain clear and stable. The space optics and telescope is testing too. Example is the 175 millimeter magnesium mirror. So the benefit of using magnesium is lightweight, high strength at extreme temps, proven durability in orbits, and compatible with high frequency signal needs. Next. Next is magnesium alloy in spacecraft energy system. Why we use magnesium alloy in energy system? We use it because it is super lightweight, about 1.75 gram per cc, high volumetric capacity about 30,833 ampere per cc, and two, two more higher than lithium. And this magnesium is rechargeable. It is because their potential for safe and efficient space for batteries. So the energy system application is first magnesium ion batteries. It is because high safety, competitive capacity, and suited for harsh space environment. Second one is thermal batteries using magnesium-based hydrates. The benefit is for cabin heating and cooling, adaptive for EV tech. And third one is hydrogen storage for space fuel cells. We use magnesium compounds store up to 40.1% hydrogen and volumetric density about 144 until 147 kilogram per mc, because it's safer and lighter than cylinders hydrogen tanks, and then ideal for full cell power spacecraft system. Next one is sustainable ceramics for future aircraft. We use graphene oxide and silicon carbide. We use graphene oxide because it is nanoscale coating, improves tensile strength and stiffness, and enhances thermal stability, while we use silicon carbide because the heat resistance or can be used in extreme temps and corrosion resistance and aerospace grade ceramics. Next, so the graphene oxide silicon carbide, aluminum, we use it because it is lightweight, high strength, fuel efficient, longer component life, better vibration and heat damping like boost comfort, safety, and engine performance. And the sustainability impact is reduce carbon dioxide emission, save fuel consumption, enable green aerospace innovation. The The graphene oxide and silicon carbide aluminum matrix is game changer for sustainable, high-performance aircraft components. Next, using next is reinforcing aircraft material with graphene oxide and silicon carbide aluminum. What's the innovation? First one, silicon carbide is high hardness, thermal stability, oxidation resistance, while carbon oxide coating is improved silicon carbide compatibility with aluminum. Combined in aluminum matrix using friction stir processing is the process. And what's the benefit of using silicon carbide and carbon oxide? First one is enhanced strength and stiffness under extreme condition, greater dimension stability at high temperatures, uniform ceramic dispersion, it is no agglomeration. Fourth one is prevents formation of brittle intermetallics. And the last one is stable for engine parts, panel, high load structure. Where it is matter, this carbon oxide silicon carbide hybrid enables lightweight yet robust composites, essential for fuel efficient and high performance aircraft system, a step forward in smart materials design. Next. Next one is we use carbon oxide and silicon carbide because the dual function it is drag plus vibration damping. Why it is matter? Because vibration damping is low fatting, high comfort and safety, crucial for turbulence, takeoff and landing phase. Carbide oxide wrap silicon carbide improves energy absorption and internal friction. So what the study found? Because the better damping than pure aluminum are uncoated silicon carbide. The higher storage modulus, especially at low temps, stable across -100 Celsius to 4000 Celsius, and the graphene oxide enhanced interference viscosity. It is mean efficient vibration control. It is ideal for whose like frames, wing support, engine mount, where the light, weight, durability, and vibration control are mission critical. Next one, we use carbon oxide and silicon carbide because it grain requirement via FISP. The grain size reduced from 160 until 4 a shift through the dynamic recrystallization during FSP, carbon oxide and silicon carbide enhance nucleation sites. It is fine aqueous grains. Where is matter because it will increase drag, decrease fitting resistance, increase thermal stability, increase corrosion resistance, and better particle is like uniform toe structure. The application is ideal for aerospace part needing high performance and durability, like outer structure, thermal shielding, and engine components. The last one is because strength enhancement with carbon oxide wrap silicon carbide ceramics because UTS increased 3.4 more than pure aluminum and 1.3 higher than uncoated silicon carbide, boosted yield strength and mechanical durability. But it's worse because carbon oxide is stronger in defense bonding, better load transfer and stress distribution, reduce grain size, it means refine the microstructure and prevent aluminum shrink gas formation because it is weak intermetallics. The aerospace benefit is ideal for load-bearing components, stronger, lighter, and more durable than traditional alloys, and reliable performance under extreme mechanical stress.
So the next, sustainable polymer materials in aerospace. Aerospace industry is being transformed by 3D printing that bio-based polymer like PLA are widely used in prototyping, lightweight, easy to process, and environmentally friendly. This polymer enable efficient designs, testing, and early stage production. The urgency to incorporate PLA and similar polymers stem not only from sustainability goals, but also the practical challenges faced in modern aircraft development. PLA enable rapid fabrication of design iteration using 3D printing technology, make it a valuable tool for engineers who need to test, revise, and optimize component design within tight, timeless timelines and budget. This is the comparison between polymers and metal. Polymers are highly flexible, allows complex geometries and quick prototyping. Meanwhile, metals are less flexible, design change are costly and time consuming. Then, polymers ideal for prototyping mocks up on non-structural and interior part, and metals essentials for structural framework design and high stress environment. Then the example of polymers like PLA are sustainable and low waste. Then ABS or PEEK are recyclable, and then we can conclude that polymers overall more eco-friendly than metals that higher environmental costs due to energy intensive extraction and processing. Then polymers like PLA has low resistance to temperature and chemicals. ABS polymer has moderate resistance to temperature and chemicals. Meanwhile, PEEK has a high resistance to temperature and chemicals. It can compare to metal that very high strength and heat resistance, critical for load bearing and engine component. Okay, uh, the other aspect for comparison about polymers versus metal is PLA. That is example of polymer is bio-based and biodegradable. Meanwhile, ABS and PEEK are synthetic polymer versus metal that are extracted from non-renewable resources. Then, polymer has lightweight, ideal for prototypes and interior parts. Meanwhile, metal have a heavier to the materials like aluminum offer a high strength to weight ratio. Then, polymer processed via 3D printing, tooling free, and rapid design iteration. Meanwhile, metals are required casting, forging, or CNC machining, inflexible to design changes. Then, polymers are fast and cost-effective, suitable for early-stage development and low-volume production. Meanwhile, metal has slow and expensive, especially when design changes require new mold for tooling. Okay, next is uh, aircraft prototyping using polymer. That one of the main application of polymer in aerospace is for aircraft prototyping. For example, a scaled aircraft model of the Boeing 737-8000 was 3D printed using polymer materials. This model helped in geometrical evaluation, dimension testing, and design visualization. Using physical prototypes improve collaboration. Uh, Engineers, designers, and even stakeholders can directly interact with the model, making it easier to spot design issues and improve the concept. Polymer also allow assembly simulation in the early stage, helping engineers identify potential design flaws before going into full production. In summary, prototyping with polymers is fast, low waste, flexible, and accessible, making it a smart and sustainable choices in early aircraft development. Besides prototyping, polymers are also used to create non-structural aircraft component parts that don't face extreme conditions or heavy loads. These include enclosures, brackets, and electronic housing. They don't require high mechanical strength, making them perfect for 3D printing during testing or pre-production. Since these parts are lightweight, using polymers also contribute to aircraft weight reduction, improving fuel efficiency and reducing emission, which align with the aerospace industry's sustainability goals. So we can know that polymer are not may not replace metal in high performance aerospace part, but they offer a real advantage in prototyping, cost reduction, and design flexibility. More importantly, they help move the industry toward greener and more efficient manufacturing. Thank you for your attention, and I'd be happy to answer any question. Wassalamualaikum warahmatullahi wabarakatuh.